Hello, and welcome to this talk on quantifying glacier change in the Patagonia Andes. My name is Dr. Varyl Thorndycraft. I'm a senior lecturer in the Geography Department at Royal Holloway. I'm a geomorphologist with a particular interest in researching how glacier and river landscapes have changed and the rates at which they have changed since the end of the last ice age. So most of my research is focused on the evolution of river and glacial landscapes over the last 20,000 years of Earth history. And I've carried out research in Patagonia for over a decade now. So just to reiterate some of the key curricula covered by this talk and the associated teaching activity. It contributes to an understanding of analysing mean rates of glacier recession. It provides an example of geospatial mapping, and of course it's a case study from beyond the UK. So in terms of the session aims, I want to show the latest understanding of global temperature change in response to greenhouse gas emissions. Our current predicament of human-induced climate heating is the global scale context to frame this particular case study. I want to demonstrate how satellite imagery has been used to quantify glacier change over recent decades, and I'll present a case study of the Viedma Glacier. The Viedma Glacier is a large outlet glacier of the Southern Patagonia Icefield. The Patagonian Icefields cover a total area of around 22,500 square kilometers with a volume of around 6,000 cubic kilometers of ice. So a large potential store of fresh water to contribute to sea level rise if there's continued melting. So let's start by looking at findings from the latest Intergovernmental Panel on Climate Change report. This report was published in 2021, and these figures are from the summary for policymakers. On the left, we've got the temperature record going back 2,000 years. This is temperature in terms of global surface temperature. That is the sort of average global temperature, including both ocean and land. It's relative to a baseline period 1850 to 1900. And the obvious thing to note is the steep increase in temperature here. So that increase in temperature is unprecedented over the last 2,000 years. And we know it is human influence that has caused this warming. We know that it is driven by greenhouse gas emissions, and the graph on the right demonstrates this from climate modeling studies. So the curve that looks a bit like the one on the left, just to point out, this axis starts from 1850, so it's a close-up in this area here, so it doesn't look quite so steep as there because it's over the whole graph is over a shorter period. But this sharp acceleration over the last 70 years or so, that is driven by known greenhouse gas emissions. If you simulate global climate just with natural climate forcing, such as solar variability, volcanic eruptions, things like that, you get a relatively flat temperature. Okay, so this unprecedented warming or heating, as we should probably call it, driven by greenhouse gas emissions. So those increases in temperature can influence glacier mass balance, and there's been significant observations of glaciers receding, including from sort of historic photographs of position of alpine glaciers in the 19th century, for example. But for a more complete way to quantify how glaciers might be changing in response to climate change, we can use satellite imagery. And here in the image on the left, there's a CGI of a Landsat 8. So Landsat is one of the longest running Earth observation satellite missions. The image shows the 8th satellite launched into orbit. In total, the record spans around 50 years. The first Landsat was launched in 1972. So the global scope of satellite imagery enables obviously a global perspective on monitoring glacier change in response to our changing climate. The image on the right is the northern Patagonian field from a satellite called Sentinel. So a beautiful cloud-free image of the northern Patagonian icefield. So increasingly there are more and more sophisticated satellites. So there are 2 Sentinel satellites in orbit, which means that compared to Landsat, they cover each point on the Earth's surface. They track more regularly, so you can get more imagery from Sentinel. We have more advanced technologies that can obtain precise topographic data, for example, on elevation of glaciers. So that's going to be beyond what we do in the exercise here, but modern satellite technology enables scientists to quantify the rate of glacier thinning, as well as just recession rates. And I'll come back to that later in the talk. So how have Patagonian glaciers responded to climate warming? We're going to focus in on the Viedma Glacier, so one of the largest outlet glaciers of the Southern Patagonia Icefield, located here. This is the southernmost tip of South America. So Patagonia is the region of the southernmost South America, and incorporates both Chile and Argentina. And as you can see, the Viedma Glacier flows out on the eastern side of the Southern Patagonia Icefield, and it flows into this large lake, also called Viedma. So, in terms of the satellite record at Viedma Glacier, the record we're going to use spans 1986 to 2018. So this slide shows the start and end point of our time series. I just want to use this to pick out a couple of observations. So the front of the glacier we call the snout. You can see in 1986 it extends further into Lago Viedma. You can see it has a kind of convex carving front and profile at this point. By 2019 you see it's now more of a concave shape. Okay, so it's the sort of morphology of the front of the glacier has changed. It could be that it's now in deeper water, for example, through this narrow channel, or it could just be that its retreat rate is accelerated, which is what we're going to look at with this time series. So we can clearly see that the glacier margin position has receded over this 33-year time span. And the other thing I wanted to point out however, is the thinning of the glacier. Now, we can't obtain precise elevation data on thinning using this Landsat imagery, but we can observe the margin of the glacier and notice some major changes. So in 1986, the glacier here is actually, the margin of the glacier here is feeding into this lake. By 2019, you see that the ice no longer flows through this bedrock ridge here. Okay, so the inference there is obviously that as the ice has receded, it is thinned. We can also see that on this exposed bedrock here. So we can see the ice much closer. It's probably in here, basically close to the vegetation. You can just see in green. You can see here the ice has thinned back down here. So we've got recession and thinning. So this slide collates all 6 satellite images that we're going to use in the activity. So you'll see for 1986, I've left the trace that I drew. So this is a digitized outline of the glacier drawn in black here around the 1986 ice limit. We can do the same for each image in the record: 2001, 2011, 2015, 16, and through to 2019. So a few observations. We can obviously see the snout receding. These first 3 images span over 20 years of the record, and then the lower 3 span the most recent decade. And I think you should be able to see just qualitatively that the rate of recession has increased. We can see carved icebergs in the Viedma Lake here on these last 2 images as well. Going back to this sort of ice contact with this small lake here, you can see the disconnection occurs sometime between 2001 and 2011. So again, from these images, you should be able to see that the ice is thinning as it recedes. So on this slide, I present on the left here, I present the 6 digitized outlines from the 6 satellite images. So there's the digitized outlines of the Viedma Glacier. These are the shape files that are provided for the activity. I've indicated how we can measure the distance of recession for the whole record from 1986 to 2019. But of course, we can do this for each individual step in the satellite time series. Each step, we can divide the distance of recession by the time interval between each successive satellite image, and that enables us to produce a graph of the rate of recession in meters per year plotted against year. So we can see there has been an acceleration in recession through the time period. There's an exceptional rate of recession 2015 to 2016, which is likely due to sort of local glaciological factors. As you see, the rate goes back to this level here, but still significantly higher than the early part of the record. I've also drawn this separate arrow on here, which extends from this moraine here that's built out into Viedma Lake. So moraine is a glacial landform. They are formed at the ice margin. So hopefully you can see here this shape here in the moraine is kind of snout of the Viedma Glacier. So the Viedma Glacier was sat at this position further out into the lake. Now, we don't have direct dating evidence for how old this moraine is, but evidence from elsewhere would suggest that the latest date the glacier started to recede from this moraine was 1860. So this is typically when glaciers started to recede. So based on a hypothesized date of 1860, we get an even smaller rate of recession prior to the satellite period. So just further evidence that over recent decades, with increasingly warming global temperatures, it looks like Viedma Glacier has increased its rate of recession. Now, those shapefiles are available for you to download. The shapefiles for the lower Viedma Glacier outlines, and I haven't mapped all moraines in the area, but some moraine deposits, they're available as .kmz extensions. These can be added to Google Earth. In fact, you can just double click the file name in File Explorer, and Google Earth will open and will take you to the Viedma Glacier. Alternatively, if you're using ArcGIS, you can use the conversion tool KML to layer to convert the shapefiles to a ArcGIS layer. And more details on that are available on the activity handout. So to finish this talk, I just want to return to the wider context. We were focusing on one glacier there. This study by Dussaint et al., published a few years ago, used ASTA satellite data, which allowed the researchers to obtain elevation data from all glaciers along the length of the Andean mountain chain. And they're able to compare glacier mass balance changes for two periods, one from 2000 to 2009 on the left here, and then the second half of the record on the right. And the use of ASTA data here, because they can get elevation data on the surface of the glacier, unlike our activity here looking at length change in the glacier, here we can get a constraint on thinning. And the scientists here were able to quantify a total mass change over this 18-year period of a loss of 22.9 gigatons per year of ice. And the most negative mass balance changes were in the Patagonian Andes. It's also worth noting that north of Patagonia here, in the first decade of the millennium, these glaciers were actually in positive mass balance, but now they have shifted to negative mass balance as well over the last decade, and this sort of links to a major drought in central Chile that's been lasting over a decade now. The second study I want to show here for the wider context is sort of expands the Dussaint study to the global scale. So here, again using elevation changes, they now quantify the spatial variability in glacier response to climate change across the world. And they identify a mass loss acceleration of 48 plus or minus 16 in terms of the errors, but 48 gigatons per year per decade. And that acceleration in mass loss across the globe accounts for 6 to 19% of the observed acceleration of sea level rise. Particularly important, they noted that thinning rates of glaciers beyond the main ice sheets, so Greenland, Antarctic, the thinning rates of those glaciers doubled over the last 2 decades. So in other words, glaciers are responding faster than the Greenland and Antarctic ice sheets. And it's those valley glaciers across the world that are contributing most at present and in forthcoming decades to sea level rise. So in summary, we have seen how the Viedma Glacier recession rate has accelerated over recent decades, and this is a pattern that fits the global picture for not only increased rate of glacier length change, but also in terms of increased rates of thinning. And if we go back to the start of the talk and the IPCC data that were presented, we can see that these changes are driven by greenhouse gas emissions. So if we want to limit further melting of our glaciers across the globe, which has important implications for sea level rise, as well as catchment scale water resources, for example, then we need to decarbonize our economies as rapidly as possible. So I hope you enjoyed listening to the talk. For more information, please do visit our website. There, as well as finding other lectures in this series, you'll also find the Viedma Glacier activity sheet and links to the shape files to download. So I hope you enjoy playing around with the shape files and exploring the landscapes around the Viedma Glacier. Thanks very much for listening.